In this lesson, we're going to talk about vectors. This is our introduction to vectors. And a vector is basically, we use them to represent both magnitude and direction. So geometrically, we call that a directed line segment. What that means is the line segment has a beginning and an end. So if I want to use line PQ, I'm going to have an arrow at Q. I start at P, I end at Q. Basically, anything that has two quantities to it can be modeled with a vector. So let's take velocity. Velocity has both speed and direction, how fast you're going and in what direction you are traveling in. So that can be modeled with a vector. Force is the same way. It's the magnitude of force and the direction. And there are others, mostly from physics, that other things that we can use to model vectors with. Those are the two main ones that we're going to deal with in this unit. So this directed line segment PQ, it has an initial point at P. That's the important part. When I say it's a directed line segment, if P comes first, then that's the initial point. And the terminal point is Q. So again, we start at P, we end at Q. And you have to go in that order. The initial point is always first, and the terminal point is always at the end. So we denote vectors by the direction and the magnitude. The direction is the angle the vector makes with the positive x-axis. We've used that before. We used that in the last unit and anytime we do trig. So what that means is if I have a vector pointing in this direction, I can denote that by measuring the angle. It's always in the positive x direction. So if I'm pointing this way, here's my angle again, just like it always has been. And the length of the line segment is what represents the magnitude. So if I got this airplane that's taken off, again, we can model that with a vector. And the length of that vector can represent the speed of the aircraft. So that's the magnitude. And the angle is the direction. And again, it all is going to come back to right triangle trig in the end. The way we denote vectors, we use lowercase letters typically. And in print, these letters are going to be bolded. You'll see that in your textbook. But when we write, we can't really bold anything, so we have to put some notation on top. And it's looking like kind of a half line or a half arrow on top of our segments to denote that they are in fact a vector. They are a directed line segment. And then finally, one more definition, equivalent vectors. Equivalent vectors have the same magnitude and direction, and location is really irrelevant when we're talking about vectors. So I can draw a series of arrows. If they are parallel and of the same length, they are all equivalent vectors. Anything that has two parts to it can be modeled in the coordinate plane. So vectors can be placed in the coordinate plane and written in terms of their x and y components. When I graph a vector in the coordinate plane, my point P will have an x and y attached to it, and my point Q will have an x and y associated with it. So there would be my vector. I could call that V. This would be x1, y1, and x2, y2. So if I want to find the x and y components, I can rewrite a vector in terms of their components. And the x component is going to be, we'll call that V1. V1 is going to be the x component. And that is the difference between the x values. V2 is going to be the y component, and that's the difference between the y values. And I can denote a vector by breaking it down in its components, and we use these fancy looking brackets. They're specific for vectors, and you will see this in your book. So I have the x component and the y component. So let's say I want to find the component form of a vector. I have an initial point of -2, 5, and a terminal point of 3, 7. So I need to take the difference in the x's. It has to be 3 minus a -2, and it has to be 7 minus 5. You have to go in that order. It's terminal minus initial. And if I want to find the x and y component, basically, it is terminal, which is 3 minus a -2. There's my x component, and it's 7 minus 5. That's my y component. So in the end, that vector u is represented by 5, 2. So let's look at vector operations. If I have two vectors, u is u1 and u2, v is v1 and v2, and c is a scalar, meaning it only has one part to it. The vector sum of u and v is going to be this. If I want to add u to v, I just add their components. So it's u1 plus v1 and u2 plus v2. I add the x's, I add the y's. Now if I want the scalar multiple of my scalar c and my vector u, that's just like distributing. So if I want to say c times vector u, then it's going to be c times u1 and c times u2. It acts like a dilation. So we can say the negation of v. If I have vector v, there should be a hat over that. If I have vector v, the negation would be -1 times vector v. So in that case, it's going to be -v1, -v2. So in that, if you do that, the difference between u and v can be converted to addition, or you can treat it like this. If I have u minus v, that's equivalent to u plus a -v. In the end, you get u1 minus v1 and u2 minus v2. So we're going to finish this lesson up with just a couple of examples, and then we'll follow up with classwork or examples in class. I have my two vectors here. I've got v is -2 and 5, and w is 3 and 4. I want to find 1/2 v. Well, that's equivalent to just distributing 1/2 through that vector v, 1/2 times those two things. That gives me -1 and 5/2. Now, if I want w minus v, again, you're going to subtract the components. If I wrote it out, it's going to be 3 minus a -2 and 4 minus 5. So in the end, w minus v ends up being 5 and -1. And that's a summary of the basic vector operations.